Excellent, excellent. Hello everybody. I'm Eric Spada, and my colleague here is Varun, Sampath. We've been working on one of the original 4, as we like to call them, documents that we were looking at when we started the OCP security group. There was the attestation, threat model, secure boot, and then recovery. And the recovery has taken a little bit of time. It's bounced a little bit around, but I think with the help of the team, we've gotten to a point where it's at the IC committee, and it's a pretty good spec at this point. So the primary part of this talk is to go through why we would want to do secure recovery in the first place, what it is, and kind of a little overview of how it's implemented. All right, so big picture. You know, we don't like to admit this as silicon vendors, but sometimes stuff fails to boot, it becomes unresponsive. You know, I know this never happens to Broadcom stuff, but I know there are other vendors that this happens to. And the problem is what do you do when this happens? And if you look at the governing document, there is a number of NIST specs. The one that is commonly referred to is platform resiliency, or what we call 193 in the security group. It defines a whole bunch of stuff. One of the things that it defines is recovery. Unfortunately, it doesn't give you any kind of guidance of how to do it, but it basically says it's really important and you really should do it. So really what we're trying to do with this is to provide a mechanism, primarily out of band. There are other ways of doing it as well, but the goal of the spec was an out of band mechanism to effectively identify that the device is in a bad state and provide a fail-safe mechanism to bring the device from this bad state into a known security state with a known signed set of firmware. So that's kind of the big picture goal. We did not replicate in the root of trust or any of the security pieces. One of the key pieces of this is the recovery image that we call it. Passes all of the operational checks from a security perspective. So it's signed with the secure boot key, has all the anti-rollback protection. It needs to be a full production image. And that was a common choice because a lot of times what happens is these old recovery images that lie around have known security, they become security vulnerabilities. You go in recovery mode and then you can attack the device. Finally, 2 other quick points is it's a minimal feature set. It was targeted to be implemented either in hardware or in ROM. Again, this is trying to get us to a point where it's a really well-known state. And we've tried to do as best we can. SM bus is a kind of wild, wild west of protocols, but we've looked at these 4 here, and we've tried to make sure that the spec it will coexist with these standards. MTCP is probably the biggest one, and also the NVMe out-of-band management perspective. As important is what we're not trying to do. One of the things is we're not replacing firmware upgrade. You should still continue to use what you're using today. This is really designed as a last resort to get the device into compliance. Okay, so so let's give you a little bit of the spec. The spec is on the OCP security wiki. There's a link 4 or 5 down. What it does is defines a basic protocol. And this protocol comes down to a couple different things. First off is to get the status and health and to figure out if the device is healthy. The next thing that it does is it goes through and allows you to download or push, which is what we call in the spec, push an image through a memory window into the device. Or as another option, you can go through and activate a recovery image that is resident on the device. That could be in ROM, it could be in other places, but one of the key things is we want to make sure that you can update that recovery image. It's a requirement in the spec to be either able to push it down, or if there is a recovery image someplace on the device, it needs to be able to be updated. And this is the same problem, to address the same problem with the known vulnerabilities in older pieces. The mechanism defines 2 things, and this was a little bit, we had a lot of discussion on this in the security group. There is 2 modes. You can go down and force the device into recovery mode. This is an optional feature. It is recommended that you can do this, but there is a number of classes of devices that have security where if the device can't be recovered, the security aspects of the device is such that you don't want to recover it, basically has to be returned and replaced. And we allow both of those in there. And then finally, probably the other big question it's designed primarily as a device spec over PCIe, but it can be done over other stuff as well. And being able to activate the image, you can either go through a reset procedure, or you can effectively just apply it, and this will allow you to do that. And that reset procedure can either be through the mechanism, or it can effectively be using a platform reset. So I think one other big thing I think we want to make sure that we cover is that depending on the nature of the device, or depending on the nature of the failure, you may not be recovered the device. If you look at the NIST specification, there's a section on what they call critical security parameters, of which they give very little guidance on, but they identify them. And effectively what they said is that if these can't be recovered, then the device cannot be moved back to a security state. So probably the easiest example of this is if you look at DICE from that perspective. DICE usually has a set of provision certificates and security state that's on flash. And this usually goes through a provisioning process in order to get that state. If for some reason that's compromised or erased, you would have to go through some type of provisioning process in order to recover that state. And we talked about forced recovery. We'd like to, it's encouraged, but it's not required depending upon the device. Okay, of course we need a good picture. This kind of gives you the big picture, how we're thinking about it. Obviously, given the platforms and how they're designed, there are different things. We define kind of 3 different pieces. A recovery agent, and this is the agent that's responsible for talking to the device and coordinating with the PA root of trust or the management controller to get the right recovery information. And then there's a recovery interface, which is actually the protocol, implemented on the device. And then there's a transport. The transport we've defined right now, it's I2C and SM bus. We've looked at I3C and USB 2, but we decided just to get the spec out and get some feedback on it. The jury is very out on what the next out-of-band interface is for these type of devices. So I think we're going to let that calm down a little bit, and we're going to do a version 2 of the dock that will address either of these 2 devices going forward. So it gives you a good idea. We see the recovery interface. There's a couple of pieces. The recovery window is how you would actually push the code in if you're going to push the image. And then there's a log that you can get the rudimentary logging information out of it. All right, at this point, I will turn it over to Varun.
Thanks, Eric. So on the previous slide, you saw the recovery agent that's orchestrating the recovery flow, and the recovery interface where that flow is responded to on the device. So this slide looks at it from a temporal view, the recovery flow, especially from that recovery agent's point of view. So the first step is to check the health of the device. For example, the platform root of trust may think the device is already misbehaving, it's not responding to certain commands. Or, for example, it might have requested an attestation report and seen that attestation report verification did not succeed. An interesting example would be that you see the measurements on the device and see that it has firmware that has a bug in its firmware update implementation. So now you can't trust the firmware update to actually update the device. This would be a case where you'd want to put the device into recovery. So next, you reboot the device into recovery mode. You could either use the force recovery mechanism if the device has implemented that, or the device could have booted to recovery mode implicitly. Say, for example, watchdog timer fired, the device reboots into recovery upon that firing. Once the device is in recovery mode, it's the responsibility of the recovery agent to push the recovery image or to program the device to pull the recovery image from whatever region it maintains. So as Eric was saying, the spec supports both a push and a pull operation. Then once the recovery image is loaded, the recovery agent tells the device to execute or activate the recovery image. And the device uses its immutable ROM to authenticate that recovery image according to the OCP secure boot specification and execute it. The recovery image then implements the full firmware update protocol. An example would be PLDM for firmware update or NVMe MI firmware update, etc. And now, after doing that full firmware update, you brought the device to full operational state. So this shows how the pieces of OCP attestation, OCP secure boot, and now OCP recovery come together to restore a device to compliance. Here's an overview of some of the commands. I'm not going to go over all of them, but they basically outline the functionality. All of these are SM bus commands, and they have arguments of up to 255 bytes in length that allow you to orchestrate things like setting the recovery image, activating it, reset, etc. And this slide is an example of how you could implement the recovery spec from a device perspective. And so there's two data flows here, going back to that PA ROT initiator slide. You have the recovery data flow to load the recovery image, and then you have the management data flow, where there would be data like attestation or PLDM firmware update, etc. And so both of these in our example here are going through SM bus pads, SCL and SDA. You see that on the left-hand side. So let's say the device needs to go into recovery. The recovery controller would be programmed to initiate loading of the recovery image. You see that on the top left with the blue arrows. And then that recovery image is passed to a secure boot controller that's implemented in the root of trust. And so that would be, for example, implemented in mask ROM as it's immutable. That authenticates the recovery image and then loads it as mutable firmware onto the root of trust. And then the root of trust implements attestation and firmware update. So then you can use management flows, for example, MCTP over SM bus to use PLDM firmware update the device. The root of trust is able to process those commands, use a SPI controller to write it to flash. Then you can reboot the device, and now it's running a full operational firmware. In terms of our call to action, we've presented to you OCP secure recovery. Hopefully it connects the dots in terms of protection, detection, and recovery in NIST 193. We'd love device manufacturers to implement it. The spec is at this 1.0 state, going to IC, as Eric said. We welcome your feedback. Open for questions.
Good morning. I know in the Trusted Computing Group, they also have a cyber resilience work group, and they discuss a lot about the design, the properties, and the processes of making recovery engines and so on. I'm curious, is there a healthy exchange between the security work group in the OCP and the Trusted Computing Group, or is it completely different scope because they're more client and IoT focused and you're more data center focused?
So,
a little bit about it?
So we have done a bunch of work with TCG. A lot of the specs that we work on with TCG around DICE and a couple of the other SPDM and a couple of mapping. We're doing another talk on that a little bit later. So we have a really good relationship with TCG, and a lot of members of the security group are also members of TCG. One of the challenges of working with TCG is it's closed. OCP by nature is open. And TCG is also a very big and very broad organization. So that's another challenge. But we try as best we can to liaison with TCG, and we had a number of very fruitful exchanges with them. This was really designed as to fit a need for the OCP community to get a standard that device manufacturers could implement that really solves a really acute problem. We would be very interested in helping move this to a full standards organization if there's interest in that. And as publishing this spec, we can figure out if there's interest in doing something like that.
So I noticed, excuse me. I noticed that your force update is optional. I think that's the right path. But do you have is there any normative or recommended ways to implement the recovery for PCIe devices?
So I think there's two choices from a big picture perspective. One of the challenges with PCIe is the whole reset domains and how they're defined in the devices. And to be honest with you, it's a little bit out of date with how devices are typically implemented. So if you have a CPU subsystem that you can reboot independent of your PCIe, it's kind of a little bit easier to think about. And the force recovery can come in and just deal with that CPU subsystem, get you the correct data down on, or the correct firmware and configuration down onto it, and then it can kind of clean up everything else. The other way to implement this is you effectively put the device into recovery mode, and then you do a platform reset.
I guess what I'm getting at is there a way to standardize the method that you force into recovery mode?
There is a set of registers in this
And
that does that.
Does the spec have anything to say about how those registers have to be separated from any compute processing on the device? I think that's the part that I'd get worried about.
So there is a bunch of guidance in the spec on how to implement force recovery in a couple of different ways.
Okay.
Take a look and please reach out to us and we'll answer best we can.
Makes sense.
So of course it's obvious to the people that wrote it and the other groups, but it would be great to have other people take a look and see if it meets the requirement.
Thank you very much.
In terms of the register bit itself, it's in that device reset command here that's in the middle of this page. And so there'll be a bit there that says force recovery on next boot of the device. And so the spec doesn't define what boot means other than you must return to an immutable trust anchor.
Okay. Thank you very much.
Yes, hi there, appreciate that. Does the spec speak about how we re-establish the chain of trust and re-attest the downloaded recovered firmware, so recovery firmware, or we need to refer to the DICE specs for that? And then maybe a second follow-up is like, suppose we have two ports on the device, so we need to separately attest both the ports if they are having access to the same physically addressable space in memory. So they need to be separately attested, considered as separate devices?
That's a great question. The last one's a great question. The first one, I think the way to look at it is there's a bunch of information in the spec on how to actually, that goes through two recovery modes. One with what we call critical data intact, which means the provisioned DICE in this example information is still on the flash. And then the second one would be where you do not have that information. If you do not have that information, you need to go through some provisioning process in order to reestablish the linkage between the two. And depending upon the customer and the environment, that could be very simple or it could be very complicated depending upon what the piece is. Now, as far as the multiple devices, I think what I understand from your question is there may be multiple components in a device. And rolling those measurements up is not really well discussed in the spec. There are a couple of ways of doing that. There's a SPDM talk later that Brett and I are going to do, and we can talk a little bit about, if you look at the platform manifest, is really the right way to look at how to attest your different pieces into the device as one possible implementation. Would you like to add anything?
Sure. I'll just add that, yeah, this is one piece of the puzzle, and that it's important to look at the OCP attestation and the OCP secure boot specs to see how you provide all three pillars of protection, detection, and recovery.
Any other questions, comments? Brian said he was going to ask a question. Why did it take so long? Is that, yeah.
Cool feature to implement it, but what is the real problem we are trying to solve here?
The real problem is if a device becomes if it becomes unresponsive, okay, and you can't talk to it, or you think that there's as the example that was given, there's a bug in the firmware update process. So you need a way per the NIST spec to get back to what they call an immutable root of trust. So what this mechanism allows you to do out of band is send the device back to a known security state and update the firmware from there.
Yeah, I understand.
Yep.
So, but the problem is how many you are seeing right now in the industry, right? The cloud storage or whoever is the platform vendor, right?
Mm-hmm.
So how many you are seeing this problem? To implementing that, how much you are going to value add to that current process?
It's a good question. I think it comes down to, from a product perspective, you need to look at, do you need to be compliant with 193? think most of the products going forward, at some level, are going to have to address this. And then you're going to have some mechanism to do recovery. Now, this is probably the most fail-safe in that it's in hardware or ROM, and it allows you a very specific set of tools in order to bring it back into the device. There are other ways of implementing recovery. If you have an ability to boot multiple images, you can do this with firmware upgrade. There's a number of other ways you can solve this, but if the device comes to a point where you have either a miss and when you update the anti-rollback counter, or there's some mechanism in that where it just doesn't boot the first mutable firmware, this is really what it's designed to address.
Yeah, a few years ago, I believe one of the OCP summits, there was a presentation talking about secure boot and said, secure boot is an architecturally specified way to denial of service your device. and so that quote has stuck with me, and this is really the foil to that, is how do you bring your device back to a state of operation?
I actually just wanted to add one comment to that last bit. If you're looking for business reasons or value adds for this, I think being able to automatically recover from a attack is a very important part of this. Someone attacks, bricks your device now, and if they do that at scale, you now have a way of forcing a recovery without having a massive.
Yeah, there's been some discussion about, there was some where they would just exhaust the replay counters. You can, and if you're not careful, there's a lot of different pieces on that. One of the things that we are working with is we're working with the OpenBMC community, and we're trying to get an open source driver. I have a couple people working on that. Hopefully we can do that. And if we get that infrastructure in place, and we've got at least 2 vendors that implement it, then it would become very automated and a very standard way of doing this through the BMC infrastructure, which is really long-term what we're trying to enable.
Okay.
So just a request, I guess. It's really hard to test recovery, right? It's really hard to test it.
Yes, there is.
Hyperscalers, cloud providers, data
Yep.
centers, you have tons of machines, you have tons of problems. You have 1 million children.
Yes.
Their own problem. And it's really hard to reproduce those conditions. So my request would be, let's hope for success here. Let's see a couple devices, but let's come back to OCP and say this is how you test it.
Yes, so one of the things that was added as a suggestion by, I think it was Ben, anyway, so there is a compliance checklist in the spec. So we kind of went through, and I think both of our teams kind of added to it as we implemented it. But if there's other things that you think should be in there, please take a look and add some comments. The other thing is if we get a reference implementation via OpenBMC, which is kind of the next step, then kind of compliance will be interoperating with that implementation is, I think, probably the best road forward.
Right. Okay, thank you.
Hey guys, good work. Quick add to this recovery command list. Are we going to add some vendor-specific commands that we can add, or?
There is options to add vendor-specific in this, and I think there actually is a specific command that's vendor-specific, and we do have in the device status and a couple other places the ability to add additional information through these commands.
Okay, thanks.
Okay, if there's nothing else, we'll move on. Thank you, everybody.